we're going to keep continuing with our analogy between voltage and height compared to electricity and gravity, respectively. Recall that a positive charge spontaneously moves in the direction of an electric field, just as a mass spontaneously moves in the direction of a gravitational field. So we might call that as down. But let's try and expand our understanding a little bit. We can imagine, say, the side of a mountain, and let's make it smooth. Let's ignore frictional effects, things like that. And where the mountain is steep, if I place a boulder on it, the acceleration of that boulder is going to be pretty large. But if the slope of the mountain is shallow, and I place that boulder there, the acceleration of the boulder will be relatively small. And this is somewhat reflective of the strength of the field. Now, it's a bit more complicated in gravity with the presence of the normal force, but in electricity, this is how we can visualize the effect of field strength. We don't have an easily visualized effect of gravitational field strength because we live our entire lives in a uniform gravitational field. But the effect is, if it's a weak electric field, the charge will have a low rate of acceleration, whereas if it's a strong electric field, the charge will have a high rate of acceleration. Either way, the charge is going to be falling, quote, down, unquote, if the electric force is the only force acting on it. There is a word that kind of describes this effect. It's called the gradient, and you might refer to a large gradient or a steep gradient to indicate that the field strength is large and imparts change in a rapid change in voltage. The relationship between the electric field and the voltage allows us to express the electric field in units other than newtons per coulomb. Newtons per coulomb are fine, but there is an alternative set. We have this relationship that this is true for a uniform electric field, that the change in voltage is equal to minus E times the change in displacement. And with a little bit of algebra, we can say that the strength of the electric field is equal to minus the change in voltage over the change in displacement, which we've examined before. But notice that we can also look at this and say that the units of the electric field are equal to units of voltage divided by units of displacement. So volts per meter are a perfectly valid way of expressing the units of the electric field. 1 Newton per coulomb is exactly the same as 1 volt per meter. I also want to stress the relationship between the electric field lines and the equipotential curves that we discussed before. Remember, the equipotential curves are somewhat like in a topographic map, the curves of equal altitude. What we have on the screen are the equipotential curves for an electric dipole. The red circle representing the positive charge, the blue circle representing the negative charge. You can see that in the very center there's a vertical line. This represents zero voltage. As we move from the vertical line towards the positive charge, we see that the voltages increase, whereas if we move from the vertical line towards the negative charge, the voltages decrease, but when I say decrease, I mean they get larger and larger, but negative. The electric field represents the direction of the force on a charge at that location. But another way of thinking about it is, if I have this charge placed in an electric field, that charge is going to move down voltage as expeditiously as possible, meaning that it is going to move perpendicularly to these equipotential surfaces down. So the direction in which the voltage is decreasing most rapidly is the direction in which the charge feels the force, meaning that the electric field line is always going to be perpendicular to the equipotential curve. I also want to discuss what's happening inside a conductor. We're going to assume that the charges are not moving. If the charges are moving, there's an electric current, and that's a horse of a different color. We're looking at the static situation where the charges are in equilibrium, they're not moving. And in a conductor, in that circumstance, all the charges are on the surface of the conductor. Even if it's made of solid copper, if I place any charge on it, the charge distributes itself over the surface. There's no excess charge in the actual volume of the conductor. So there's no electric field inside the conductor. And so it's not that there's zero voltage inside the conductor, it's that the change in voltage inside the conductor is zero. If you wanted to visualize it, think of it as a mesa, which is a geographic feature in which there is a relatively flat top, like you see in the picture. The altitude changes until you get to the rim of the mesa, and at that point in time, the height more or less stops changing. Well, that's sort of what's happening with the charge on the surface of a conductor. As you get closer to the object, your voltage increases. But once you reach that surface, if you start moving inside the conductor, the voltage stops changing. It's just going to hold on to that voltage that it has at the surface. If I wanted to plot the electric field strength as a function of distance from the center of a charged conducting sphere, there's no electric field on the inside. But on the outside, the electric field goes as kq over little r squared. On the other hand, the voltage inside doesn't change. It remains constant, but once you reach the outside of the sphere and start moving away, the charge will drop off as 1 over r. Now that we have hopefully a more thorough understanding of voltage, we want to go back to the original rationale for it as a way of calculating electric potential energy. Electric potential energy equals charge times voltage. The electric force is a conservative force, and because it's a conservative force, we can plug it into the work energy theorem as an additional term. If you remember from Physics 140, the work energy theorem, one variation of it says that the work done by non-conservative forces equals the change in kinetic energy plus the change in the potential energy of conservative forces. What I've done on the screen is I've more or less written that out. We see work done by non-conservative forces on the left-hand side, but we see change in kinetic energy, 1/2 m little v final minus 1/2 m little v initial squared. We also see change in rotational kinetic energy, 1/2 I omega final squared minus 1/2 I omega initial squared. We see change in gravitational potential energy, which we're assuming is near the surface of the Earth. So plus mgh final minus mgh initial. We have change in elastic potential energy, 1/2 kx final squared minus 1/2 kx initial squared. And then finally, we have the change in electric potential energy, Q times capital V final minus Q times capital V initial. Now, I would never, ever give you a problem in which all of these things are happening at once. And in fact, I'm not going to be dealing with springs at all in Physics 150, nor am I going to be dealing with rotational kinetic energy at all in Physics 150. So you don't need to worry about that stuff. On the other hand, I reserve the right to worry about changes in kinetic energy, regular linear kinetic energy, gravitational potential energy, and electric potential energy. So in principle, all three of those things could be happening simultaneously. But don't worry about rotational and elastic. Let's take a look at an example. We have a 69.3 nanocoulomb charge with a mass of 1.83 milligrams, and it's moving through a uniform electric field. We see this notation, positive 6,780, and then we see this J hat. This is the way that engineers like to express their vectors. J hat means in the y direction. So we have positive 6,780 in the y direction. The problem says the particle moves vertically from negative 5.11 meters to negative 1.23 meters. It says the initial velocity is 0, and there is a total of 92.1 millijoules of work done by non-conservative forces on it. And the question is, what is its final speed? Once again, I want to remind you that milligrams means that you got to move your decimal point over 6 places. You got to change it by a factor of 1 million. So 1.83 milligrams is 1.83 times 10 to the negative 6 kilograms, or 0.000000183 kilograms. Do you think I'm going to give you milligrams on the test? It's probably a safe bet. We have the particle moving in a uniform electric field, so we can calculate the change in the voltage. The change in the voltage is going to be minus the field strength times the change in displacement. And the field strength is 6,780 volts per meter. And the change in displacement, final minus initial, negative 1.23 minus negative 5.11. We get that the change in voltage is negative 26,306.4 volts. We're going to plug that into the work energy theorem. And we're going to ignore the gravitational effect because the mass is so small. We get that the work done by the non-conservative forces, 92.1 millijoules, is equivalent to 0.0921 joules. And then we have the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared, although we're told that v initial is 0. Then we have Q times capital V final minus capital V initial, which is the same as saying Q delta capital V. The charge is 69.3 times 10 to the negative 9, and delta V is negative 26,306.4. We keep plugging away. We get ultimately that the final velocity squared is 102,648, and therefore the final velocity, we take the square root, the final velocity is 320 meters per second. Moving on. I want to discuss a device that is used in electric circuit designs that stores electric potential energy. This device is called a capacitor. And I want to start examining a capacitor by looking at parallel plates. What we can do is we can move charges from some source onto a plate. And now imagine these two parallel plates made of conducting material that are separated from each other by a gap. I dump positive charges onto one plate, and I dump negative charges on the other plate. The positive charges on one plate are attracted to the negative charges on the other plate, and vice versa. So there is the ability to start storing charge on these plates, and this charge storage is stable for relatively long periods of time. This device is called a parallel plate capacitor. We can imagine trying to dump charge onto a parallel plate capacitor. And the first charge on there, if we start with a neutral parallel plate capacitor, the first charge on there is placed there with no problem. Subsequent charges, the prior charges placed there try to repel these additional charges that we dump onto the plate. But remember that there is also this attraction with the negative charges on the opposite plate. So it winds up being a balancing act. The amount of charge on the positively charged plate is attracted to the charges on the negatively charged plate, but all those positive charges on the positively charged plate are trying to repel each other. So there's this balance between the repulsion and the attraction, but we can still reach an equilibrium state in which we have positive charges on one plate and negative charges on the other plate. The property of this plate that is used in calculations is called capacitance, and we'll see that it's represented by a capital C. So let's build up to it. We have this parallel plates. We have positive charges on one plate and negative charges on the other plate. Therefore, we have a voltage difference across the plates. And if we have a voltage difference across the plates, we have an electric field between the plates. The electric field between the plates can depend upon the area of the plates and the amount of charge on the plates. Naturally, the more charge we put onto the plates, the greater the electric field strength between the plates. But there's also an effect of the surface area of the plates. If I allow these charges to spread out over a plate with a very large area, then the effect is going to be somewhat diluted. The potential difference is without that concentration. The electric field strength in between the plates is relatively weak, and therefore the difference in voltage from one plate to the next plate will be relatively small. So we see that the potential difference is dependent upon the amount of charge we dump onto the plate, but it's inversely proportional to the area of each plate. There's also the question of the separation between the plates. When we calculated the electric field strength for a parallel plate, the separation wasn't an issue. But consider that the potential difference depends upon the electric field and the distance over which this electric field is applied. The greater the separation between the plates, the greater the voltage difference from one plate to the next. So when we combine these, we get that the potential difference is proportional to the charge, it's proportional to the separation between the plates, and it's inversely proportional to the area of the plates. So it's more or less looking like this. We have the narrow separation on the left, we have the large separation on the right. The electric field strength between these plates is the same, whether it's the situation on the left or the situation on the right, but delta X on the right is bigger, and so the voltage difference will be bigger for the situation on the right. As for the area, we see the same number of field lines on the left and on the right, but on the left, the field lines are clustered more tightly together than on the right. And recall that when electric field lines are dense, that means that we have a strong electric field. So we have a strong electric field in between the narrow plates. The plates on the right have the same amount of charge, but the electric field in between them is weak. The geometric properties of the plates, the cross-sectional area of each plate and the separation between these plates in particular, give us the capacitance of the device. The capacitance of the device is a property of the device. Therefore, it exists whether or not we've decided to place charge on it. The capacitance depends only upon the physical properties of the plates, not on the amount of charge that we've actually stored on the plates. And so we get this quantity right here. The capacitance, which is a property of these parallel plates, depends upon the area of a plate, capital A, and it depends upon the separation between the plates, D. And epsilon naught exists as our constant of proportionality. This property of parallel plates, capacitance, is measured in units of farads, and the farad is named after a British scientist by the name of Michael Faraday, and this is not the last time in this course that we're going to be mentioning Michael Faraday's name. With this definition of capacitance, Like I said, the capacitance exists whether or not we have charge on the device. But once we place charge on the device, we now have a voltage across the device. And the relationship between these three quantities is that the magnitude of the charge on a plate is equal to the capacitance times the voltage difference across the plates. We can look at a plot of charge versus voltage, and you might wonder why, but let's hold off. If we look at a plot of charge versus voltage, as voltage goes up, charge goes up, or as charge goes up, voltage goes up. And in this slope of charge on the vertical axis and voltage on the horizontal axis, the slope is C. Now, I include this plot because recall that potential energy goes as charge times voltage. But if the charge is varying as a function of voltage, like we see in this plot right here, I can't just say charge times voltage. In fact, instead what I'm trying to do is basically finding the area underneath this plot. If I want to build up a certain amount of charge, it's going to take some effort. I have to keep adding charge. I'm doing work on the system. That work is getting stored in the potential energy in the charges on the capacitor. And because adding more charge becomes harder and harder with each additional charge, I get this effect right here, and I'm going to have to use area underneath the curve. The area underneath the curve is 1/2 base times height. The base is the voltage, the charge is the height, so 1/2 QV. But remember, we also have the relationship between Q and C and V. Q is equal to CV. So I could say that the work is 1/2 CV squared, or I could say that the work is 1/2 Q squared over C. Each of these three expressions, no matter which one you use though, is going to tell you how much electric potential energy is stored in the capacitor. Let's take a look at this example on the screen. We're asked for the capacitance of a parallel plate capacitor, not capacity. So let's just take a moment and fix that. Capacitor. And the plates measure 2.77 millimeters by 2.77 millimeters, so they're square. And they're separated by 0.315 millimeters. And the strength of the electric field between the plates when 7.93 volts is applied, we want to determine the strength of that and the magnitude of the charge. So we have our work cut out. We want the capacitor, we want the electric field strength, we want the charge, given the numbers on the screen. Our area, after we convert our measurements to standard units of meters, our area is 7.6729 times 10 to the negative 6 square meters. And the separation in standard units is 0.000315 meters. This allows us to now calculate the capacitance. Remember that the capacitance equals epsilon naught times A over D. So epsilon naught, 8.854 times 10 to the negative 12. A is 7.6729 times 10 to the negative 6 square meters. D is 0.000315 meters. Plug it all in, I get 2.08 times 10 to the negative 13 farads. And if I convert that into metric prefixes, I can say it's equal to 0.208 picofarads. And picofarads, nanofarads, microfarads, those are pretty typical measurements for real-life capacitors. The electric field in between the plates is uniform. So the electric field is equal to minus the change in voltage divided by the change in displacement. And the change in displacement is simply the gap between the plates, which we called D. So So the electric field goes as minus the change in voltage divided by D. We're given that the change in voltage is 7.93 volts, and we're given D, the separation, is 0.000315 meters. So we get that the electric field is negative 25,200 volts per meter, but we're asked for the strength, so we just take the absolute value. The electric field strength is 25,200 volts per meter. And then the charge, Q equals C delta V. Q is going to be equal to 2.08 times 10 to the negative 13 farads times 7.93 volts. And that winds up being equal to 1.65 times 10 to the negative 12 coulombs, or 1.65 picocoulombs. So perfectly ordinary amount of charge for one of these tiny capacitors. That's enough. We'll pick up in class, and hopefully some of this will make sense. Bye-bye.